All right, so we're just going to practice these trig equations and inequalities today. So our first set are equations, which means we should be doing the plus 2 pi k idea. And the first one, I have the same type of trig function in two terms, so I'm going to factor out what I can. So factor out a cosine of 2x, and you're left with 2 cosine 2x plus 1. I didn't use any double angle identities because I don't have a mix of sine and cosine here that I need to get to match. So then cosine of 2x could equal 0, or cosine of 2x could equal negative 1/2. If cosine is equal to 0, that's happening at our non-quadrant angles at the top and the bottom of the circle. So 2x could equal pi over 2 plus 2 pi k. Or 2x could equal 3 pi over 2 plus 2 pi k. And then when we divide by 2, or think of that as multiplying by 1/2, we get x equals pi over 4 plus pi k, where k is an integer. So that's the first solution set. And then we also get, when we divide by 2 again, we get that x equals 3 pi over 4 plus pi k. And k is still an integer. To save room on this paper, I think I might just do a general k is an integer for all of these. Okay, and then the second part of the answer, cosine is equal to negative 1/2. It's negative in quadrants 2 and 3. The reference angle you should be using is pi over 3. And we get 2x equals, in quadrant 2, that's 2 pi over 3 plus 2 pi k, which gives us all the coterminal angles to 2 pi over 3. So x would equal divide by 2, or multiply by 1/2. 2 pi over 3 times 1/2 is going to be pi over 3 plus pi k. Also, 2x could equal, in quadrant 3, it's 4 pi over 3 plus 2 pi k. Divide by 2, multiply by 1/2. So x equals, again, 4 pi over 3 times 1/2, that'll be 2 pi over 3 plus pi k. So make sure you're reducing. You can either say this is 4 pi over 6 and then reduce, or I like to divide first. 4 divided by 2 is 2 pi over 3, but either way. And again, k, just to save room on this worksheet, k is an integer for all of these. Okay, number 2, I see 4 terms, so that means I should be trying to factor by grouping to see what happens here. So in the first group, I can take out a greatest common factor of 2 sine squared x, which would leave me with 2 sine x plus 1. In the second group, I can take out a minus 1, which would leave me with 2 sine x plus 1. So factor by grouping works here because we have a common factor of 2 sine x plus 1 in both terms, and that means you can group together 2 sine squared x minus 1. If 2 sine x plus 1 equals 0, then sine x equals negative 1/2. If 2 sine squared x minus 1 equals 0, then sine squared x equals 1/2. So remember to square root this. We've had this a few times in our homework now. So sine x will equal plus or minus 1 over radical 2. So in the first scenario, we should be looking at quadrants where sine is negative, so quadrants 3 and 4, and the reference angle is pi over 6. In the second equation, we should be looking at all 4 quadrants, and the reference angle is pi over 4. So our first solutions from the first part are going to be x equals, in quadrant 3, it's 7 pi over 6 plus 2 pi k. And in quadrant 4, it's 11 pi over 6 plus 2 pi k. And then over here, we need all 4 of the pi over 4 angles because of the plus or minus. So x equals pi over 4 plus 2 pi k, 3 pi over 4 plus 2 pi k, 5 pi over 4 plus 2 pi k, and 7 pi over 4 plus 2 pi k. For all of these, k is an integer. The plus 2 pi k is just giving you all of the coterminal angles to that angle. All right, now number 3, I can't factor a cosine x out as this is because one of these is cosine of 2x, and I can't combine like terms because they're not the same. So this is one where you need to use your double angle identity. Now, I could use cosine squared x minus sine squared x. But remember, we have these alternate forms. I don't want to introduce necessarily two trig functions. I mean, I guess I could. I guess there are a couple of ways you could go on this. Let me see what I posted in the homework before I go into this for my answer key. I guess I could do this. So I did cosine squared minus sine squared, and then I did change sine squared to 1 minus cosine squared. But remember, you can also just say cosine of 2x is equal to 2 cosine squared x minus 1. So I'm going to make this jump right away because we have these alternate forms, if you have them memorized, of cosine of 2x. And I would want to use this one because I see cosine here, so I want everything to match. Okay, so when I do this, I'm going to use the 2 cosine squared x minus 1 option for cosine of 2x, rather than the original cosine squared minus sine squared. But if you check the key that I posted on Schoology, you can see me do it the traditional way where I just do cosine squared minus sine squared, and then I still make that substitution. I get here in the end anyway. Okay, so I'm going to rearrange this so that it's in a trinomial format to make things easier to factor. This is a trinomial, so we should be splitting up 2 cosine squared into 2 cosine x and cosine x. The only way to split up 1 is 1 and 1. You need to get the signs right, so it's got to be plus and then minus, because if you were to distribute this back together, you would get negative 2 cosine x plus cosine x. That's going to give you negative 1 cosine x in the middle. So the first factor means that cosine x would equal negative 1/2, and the second factor would mean that cosine x would equal positive 1. Cosine is negative in quadrants 2 and 3, and the reference angle to make cosine 1/2 is pi over 3. So x equals 2 pi over 3 plus 2 pi k, and 4 pi over 3 plus 2 pi k. When is cosine equal to 1? This is one of the non-quadrant angles, and the only coordinate around these four that has a positive 1 x-coordinate is at 0. So instead of saying 0 plus 2 pi k, I'm just going to say x equals 2 pi k. Again, k is an integer for all of those. And last equation to solve, tangent squared minus 3 equals 0. So we can isolate tangent squared here by adding 3 to the other side. We need to square root both sides. So tangent x is plus or minus radical 3. And remember, that's like radical 3 over 1. So when you're thinking of the question is it pi over 6 or pi over 3? So here are the pi over 6 coordinates, pi over 3 coordinates. All right, so which one of these y over x combinations do I want? It's right here at pi over 3, where y has a radical 3 in the numerator and x has a 1. So the reference angle here is pi over 3, and because of the plus or minus, we want all four quadrants. So x is going to equal pi over 3 plus 2 pi k, and 2 pi over 3 plus 2 pi k, and 4 pi over 3 plus 2 pi k, and 5 pi over 3 plus 2 pi k. Now, when we do inequalities, we're not giving infinite answers. We're just solving between 0 and 2 pi. So we're going to use just non-calculator on these. This says, remember to plot places where the function is undefined if applicable. So really that just applies to tangent, cotangent, secant, cosecant if we had them. All right, so when is cotangent x less than or equal to radical 3? So when is cotangent x equal to radical 3? So I just drew these ordered pairs over here. Let's use these. One is the x over y, radical 3 over 1. That's at pi over 6, when x over y is radical 3 over 1. So x equals pi over 6, and then also in quadrant 3, 7 pi over 6. Those are the two places cotangent's positive. But we also need to think about when is cotangent of x undefined. And remember, that is when your x over y is 1 over 0 or negative 1 over 0. Or think about the cotangent graph. It had asymptotes at 0 and pi. So at 0 and pi, and 2 pi, I guess, those will be where we have asymptotes. So I like to have both a number line and a little unit circle here. The unit circle helps me figure out which angles to place between these marks that I'm going to mark off. So 0 is one of our asymptotes. Pi over 6 is somewhere. I'm not real worried about distance here, placing these correctly spaced apart. Pi would come before 7 pi over 6. And then we have to end at 2 pi. So we need to pick numbers in between all of these spaces to test into our inequality, and we always test into our isolated inequality. And I use the unit circle to help me kind of think about that. So we've got 0, we've got pi over 6, pi is over here, 7 pi over 6, and 2 pi. So we need something between 0 and pi over 6, something between pi over 6 and pi, something between pi and 7 pi over 6, and something between 7 pi over 6 and 2 pi. Now, we can't plug in 0 or 2 pi like we normally do because cotangent's undefined at that value, so we'll have to get a little bit creative here and kind of think about things. Something between pi over 6 and 2 pi, I'm just going to pick something like pi over 12, and we'll talk about that in a minute. But I want to set all of my other values too. So how about pi over 2? Seems like a nice, easy point. And then I'll do kind of the same thing here. Like I want 1 and 1/12 pi, so like 13 pi over 12. And then maybe 3 pi over 2 would be good. All right, so in here we're thinking, what about what's happening at pi over 6? So what is the cotangent of pi over 12? And is that less than or equal to radical 3? Now, I know that the cotangent is the x-coordinate over the y-coordinate. And here the x-coordinate at pi over 6, the x-coordinate is radical 3 over 2, and here the y-coordinate's 1/2. Out here, the x-coordinate is larger and the y-coordinate is smaller. It's kind of hard to think, like, I don't know, is that going to come out less than radical 3 or not? Well, as we're getting closer to pi over 2, we know that cotangent's approaching 0. As we're getting closer to 2 pi, or to 0, we know that we're approaching an asymptote. Let's think about the cotangent graph. Maybe that'll be easier. Here's 0. Here's pi. The cotangent branches go like this. So I think graphically might be the best way to think about this. So here's pi over 4. Pi over 6 is like somewhere here. Pi over 12 is even higher up. So, so is the cotangent, I get this off my screen, is the cotangent of pi over 12 higher or lower than the cotangent of pi over 6? I think that it's higher, right? It's going to be closer to this vertical asymptote. So this is some higher number. I don't know what it is exactly. Is a higher number than radical 3 less than or equal to radical 3? No. So that's really hard to think about. This is a pretty challenging problem. Sometimes these work out nicely. And sometimes we really have to sort of hurt our brains a little bit to think about this if the angle that we're choosing, that we have to pick in between something, is not one of our common angles. It should be much easier for us to evaluate. My next value is pi over 2. What's the cotangent of pi over 2? That's one I know and can compare to radical 3. Cotangent of pi over 2 is 0, which is definitely less than or equal to radical 3. So this is part of the solution set. Next one, again, a weird one. Cotangent of 13 pi over 12. Is that less than or equal to radical 3? So let's think about this again. We're just on the next branch of cotangent. So here's the next branch of cotangent. And by the same kind of rule that I used last time, pi over 6 is somewhere to the left of pi over 4. Here's pi over 6 on the graph. Here's the, or not pi over 6, but pi plus pi over 6. Here's pi plus pi over 12 on this section of the graph. So the same thing's going to be true. This is something higher than radical 3. That's definitely not less than or equal to radical 3. So nope. These do tend to alternate, but not always. So it's good to do the math and kind of check. And my last one should be easy again. I'm going to use 3 pi over 2. The cotangent of 3 pi over 2, is that less than or equal to radical 3? 0 less than or equal to radical 3. That is true. So here's a section as well. So our solution set is pi over 6. Oh, I should be including pi over 6 because this is equal to. And I should be including pi and 7 pi over 6. So pi over 6 to pi. And then also 7 pi over 6 to 2 pi. And the only reason I'm not including 2 pi is because we have vertical asymptote there, but also we don't include it in our solution set because 0 is coterminal to 2 pi. All right. Cotangent and tangent problems are much more challenging than cosine or sine. So let's take a look at this. Isolate first. Cosine of x is greater than 1/2 if I divide by 4. Okay, so there are no undefined things to consider. Cosine is 1/2 when x is pi over 3. And then in quadrant 4, 5 pi over 3. So our number line still starts at 0. I'll mark off pi over 3 with an open circle because this is greater than. 5 pi over 3 is somewhere over here, open, and 2 pi is where we end. I'm still going to do a unit circle to help me correctly pick my angles in between. Just think that's a nice visual. So 0, pi over 3, 5 pi over 3. So we have a lot of freedom in here to pick values in between what we have marked off. So we need something between 0 and pi over 3. So that could be pi over 6 or pi over 4. Or you could still just plug in 0 probably. Actually, I think I'll do that. Anytime I can plug in 0, I do. The only time you can't plug in 0 is if you get undefined. So we'll plug in 0 there. And then anything between pi over 3 and 5 pi over 3, you could pick pi over 2. You could pick pi. 3 pi over 2, doesn't matter. I'm going with pi. And then something between 5 pi over 3 and 2 pi. Again, you could pick 2 pi, or you could pick something in that section there. So cosine of 0, is that greater than 1/2? Cosine of 0 is 1, which is greater than 1/2, so yes. And then something in here, I picked pi. Is cosine of pi greater than 1/2? Cosine of pi is -1, which is not greater than 1/2, so nothing in that section. And by the way, if you would have picked pi over 2 or 3 pi over 2, 0 is also not greater than 1/2, so same conclusion. And again, I could pick the pi over 4 angle here, the pi over 6, or I'll just do 2 pi again. Cosine of 2 pi is 1, which is greater than 1/2. And so I'm shading this section as well. Now at 0, the cosine of 0 is definitely bigger than 1/2. So we are including that in our solution set because we're including 0 here. So 0 is not one of the numbers that where cosine was equal to 1/2, so it doesn't have to have an open circle. So 0 to pi over 3 and 5 pi over 3 to 2 pi. All right, that finishes this worksheet. Come see me in office hours if you have questions.